Acid-base titrations. And I'm on the wrong slide already. There we go. We've talked about stoichiometry, and we can apply our knowledge of solution concentrations and do stoichiometry with concentrations and apply that to a technique called titration. Titration is a laboratory technique in which a substance in a solution of known concentration is reacted with another substance in a solution of unknown concentration, with the goal of finding out what the unknown concentration is. Oh, and there's another typo. The slides are horrible, sorry. So this is frequently done with acids and bases. And so if we look at the reaction between hydrochloric acid and sodium hydroxide, we find that the net ionic reaction for that is hydrogen ion plus hydroxide ion is forming water. And we can illustrate the hydrochloric acid solution like this. We really don't care about the chloride ion because it's a spectator and it doesn't do anything. The hydrogen ion is what does something. And remember, we talked about hydronium ions and hydrogen ions and how these hydrogen ions are really not running around by themselves. They're riding piggyback on a water molecule, but it's just simpler to talk about them as just individual hydrogen ions. So this is an illustration of a solution of hydrochloric acid. We're just looking at the hydrogen ions because that's what's going to participate in the reaction. So in all of these diagrams, we're going to leave the sodium ions and the chloride ions out, and they don't mind. So what happens in a titration is you take a solution of known concentration, and here this would be the sodium hydroxide, and we use a fancy piece of glassware called a burette, and we'll get to use those the week after Thanksgiving in lab. So there's sodium hydroxide in here, and so we're just looking at the hydroxide ions in this burette. And down here in the flask we have our hydrochloric acid solution. We know the concentration of the sodium hydroxide. We don't know what the concentration of the acid is. And so what we're going to do is we are going to add sodium hydroxide to this, and a reaction will occur. So as we add hydroxide ions, they react with the hydrogen ions in solution. And eventually we'll get to an equivalence point where the number of moles of hydroxide ions added is equal to the number of moles of hydrogen ions present in the solution. That's a stoichiometric ratio. So we've got the correct number of moles. Well, how do we know when that happens? We use an indicator. And we'll talk about that in a minute. But that's the idea. We're going to add this known solution to this unknown solution. And the burette allows us to accurately measure the volume of that, and we know the concentration. The molarity. If we know the molarity and we know how many liters, we can calculate the number of moles. We know how many moles we added here, and that equals the number of moles of hydrogen ions. And so we can figure out the moles of hydrogen ion that way. The equivalence point is where you've added equal numbers of moles, or stoichiometric ratio of moles. How do you know when that happens? Well, we use an indicator. An indicator is a dye whose color depends on whether the solution is acidic or basic. And so we measure carefully the volume of each solution, and we know the concentration of one of them. We add them until the reaction is just complete. The indicator changes color and tells us that, and then we can figure out the concentration of the unknown solution. So here are pictures, not just illustrations, of what's happening here. We've got a burette with sodium hydroxide, and we've got a flask with hydrochloric acid. And this also has indicator in it. Phenolphthalein, that's a fun word. Phenolphthalein. This middle pH you can kind of think of as being silent. Phenolphthalein is an indicator. It's colorless in acidic solution, and it turns pink in basic solution. Actually, kind of this color. This is phenolphthalein colored sweater I'm wearing today. That was unplanned and random. So as we add sodium hydroxide, we see a little bit of pink form here because the sodium hydroxide does not immediately react it doesn't immediately mix. And so right here, there's a higher concentration of hydroxide ion, and so it turns pink. And then as we swirl that and mix it, it comes in contact with more hydrogen ions and reacts, and it goes clear again. And we keep adding and adding until we get to the point where just one more drop and the whole solution turns this nice pale pink. You don't want to get it real bright pink because that means you went too far. You want to go the first pink color, and that tells you you've added just a tiny bit more hydroxide ion. Tiny bit more. It's the best we can do. So let's do an example. So the titration of a 20 ml sample of a sulfuric acid solution of unknown concentration requires 22.87 milliliters of 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown sulfuric acid solution? That's a lot of stuff there, isn't it? Well, we're not given a balanced chemical equation, but it really helps to do a balanced chemical equation. So what are we reacting here? We're reacting sulfuric acid and KOH. And so we should be able to do that. So sulfuric acid, H2SO4, it's a bad S, H2SO4 plus KOH. We've got an acid and a base, and what are they going to form? Water and salt. So I'm going to do some scribblings down here and then I'll erase them. But the sulfuric acid, the ions present there are H plus and SO4 2 minus. And in KOH we have K plus and OH minus. Acid-base neutralization reactions can also be thought of as double replacement reactions where the partners are swapping. And so we end up with water, that's the H plus and OH minus getting together. That makes water. And then those other two ions will be the K plus and the SO4 2 minus. So we need to consider their charges when we put them together. Potassium has a +1, sulfate has a -2. So we need K2SO4. So those are our products. And then we need to make sure the equation is balanced. Is it balanced? No, it isn't. On the right side, we have 2 potassiums, and on the left, we have 1. So we need to put a 2 here. And on the left side now, we have a total of 4 hydrogens, right? 2 from the sulfuric acid and 2 from the 2 KOH. And on the right, we only have 2, so we need a 2 in front of the water. And then if you look at it, you'll realize that that took care of the oxygen. Okay, so that's just a brief review of a previous chapter. And kind of an example of why the final is cumulative, because some of these questions, it's almost impossible to ask them in a way that's not cumulative, because this is something we learned before. Now we have an equation, and the equation, like when we did other sorts of stoichiometry, will help us organize this information. So we read the question, 20 milliliter sample of sulfuric acid. Okay, so that's a piece of information about the sulfuric acid. So write 20.0 milliliters under the formula for sulfuric acid. And that's an unknown concentration. And it says we need 22.87 milliliters of the KOH. So write that over here, 22.87 milliliters of KOH. And the concentration of the KOH is 0.158 molar. 0.158. Now I was getting into concentrations with my class at Reedley College, and I realized this might be a kind of a good rule of thumb. You see the capital M in the question. Just get in the habit of never writing it down. When you see capital M, write down moles per liter, because otherwise you're going to forget what it is and you're going to have problems. So capital M, that means moles per liter. Don't write capital M. And then what is the concentration? So the question here is question mark moles per liter of the sulfuric acid solution. That's what we're trying to find. Any questions about how I pulled that out of the words? Everyone can learn how to solve word problems. It's more challenging for some people, but you can do it. Telling yourself you can't will not help. Okay? I know it's challenging for a lot of people, but you can do it. Okay, so now what do? Well, titrations are stoichiometry. So what was our path for stoichiometry? I'm going to write it up here on the top. Grams to moles to moles to grams, right? So grams to moles to grams. Are we going to be able to start with grams and end with grams here? No. This is a variation. All of these problems will have mole to mole in the center, but sometimes one or both of the ends will be a little bit different. So what are we given? We're given volumes of both of them, and we're given a concentration of 1. So we're going to have to use those sorts of numbers. So we've got a concentration and we have volumes. So look at the units. One of them is milliliters, the other is moles per liter. Anytime there's per in the unit, that's probably supposed to be used as a conversion factor, and that's not where you're going to start. So what we're going to do here is we're going to start with volume. So we're going to go from volume to moles. And then from moles, what do we want to end up with? We want to end up with the concentration in moles per liter. There's a couple of ways you can think about this. You can string it all together, or you can look at, okay, well, what is the concentration? It's moles per liter. That means I need to know the number of moles and I need to know the number of liters. So it might make sense to you to do this stoichiometry and stop at moles and then divide by liters. I'm going to go ahead and just do the whole thing. So I'm going to go here from moles, I'm going to go to moles per liter. I'm trying this new thing with this pretty blue bar up here, but then it kind of restricts how much room I have to deal with anything, so I'm not sure if I like that. I got a little bored. You got to have some fun when you're doing these stupid slides. They're not stupid. Yes, they are. So then what are we going to start with here? The 20 milliliters or the 22.87? The 22.87, because we know the concentration for that one, which will allow us to change the volume into moles. So we're going to start with 22.87 milliliters of KOH. And then our path said we're going to moles of KOH, and then to moles of the other thing, moles of H2SO4. And then we want to end up with moles per liter. Well, let's look at these first ones. Milliliters. For now, we're going to ignore the difference between milliliters and liters, because what I'm going to show you is that the conversion cancels out. All titrations are pretty much done in milliliters, because liter as a unit of volume for a regular chemistry experiment is way too big. So we measure things in milliliters. And since they're both measured in milliliters, you can prove it to yourself. You can change this to liters and do the calculation, but then you're going to have to change, and it's going to cancel out. So just for now, humor me and Yeah, there's milliliters there. I'm going to put liters down here. And maybe this is a bad way to show it to you, but we'll find that out, won't we? And then down here, we're going to have moles of KOH. And those cancel out. These, the milliliter doesn't cancel, but the liters of KOH cancel. So we're left with that random milli over there. Moles of sulfuric acid. What do we need to do to the units to get moles per liter? We just need to divide by liters, right? So, what, oh, good grief. It's so beautiful, and yet it just doesn't work so great with the pattern I showed you. Okay, don't cancel out those units. We have the volume here in milliliters, and so let's just throw it in there. And I'll probably do this different in Readly, and then you can watch that video and not be confused. We'll see how this goes. Moles of KOH per liters of KOH. That's given to us. And the 0.158 is with the moles, so it goes with the moles here. 158, I didn't leave enough room. What's the ratio here, moles of sulfuric acid to moles of KOH? It's from the equation. What's in front of H2SO4? An implied 1. What's in front of KOH? A 2. And then over here, what's in the numerator is just the number 1, and then the volume of the sulfuric acid goes down here. Now look at those units. These milliliters are canceling those milliliters. The KOHs cancel each other out. And what we end up with here is moles of sulfuric acid per liter of sulfuric acid. So this is a more elegant or sophisticated way of doing it, which may not be the best way for you, but I'm going to show it to you. So 22.8 times 0.158 divided by 2 divided by 20. And there's not enough room to write it there, so we'll write it up here. How many significant figures should this number have? 4 or how about 3? Because 0.158 has 3 and 20.0 has 3. 22.87 has 4. I'm not sure why the 20 doesn't have 4, but that's how they wrote it. So we're going to have 3 sig figs, so I'm going to round this off to 0.0901 moles per liter. That is the concentration of the sulfuric acid. Did that make any sense? A little bit. Did my tricks with the units mess you up? Not really? Anybody? Do you want me to see it? Do you want to see it the other way?
I didn't know you could do that. I didn't know you could just do milliliters.
Yeah, that's what I was thinking. When was thinking.
But I didn't know you could do that.
Yeah. So you can do that.
Where does the liters cancel out again?
Well, here, let's do this. I will cover up all these nasty words here.
Wait, you have liters somewhere on the top, don't you?
On the bottom.
Oops.
No. Oh, so milliliters canceled out.
No liters canceled out, no. The milliliters did. So let's just make some room here and do it again. We'll make this. So if here we're going to start with 22.87 milliliters, and we're going to convert to liters. So that would be 10 to the minus 3 liters per milliliter. the milliliters cancel out. And then we're gonna go to the 0.158 moles per liter, and the liters cancel out. And then we're gonna do the 1 mole KOH per 2 moles H2SO4, and the moles cancel out. No, that's, sorry. Okay, back up. Because what's wrong with that? I put the things in the wrong place. Like, wait a minute, H2SO4 goes on the top. 2 moles of KOH, that's better. So the moles cancel here. And then, so now we've solved for moles of sulfuric acid, and we need to divide by the volume, which is 20.0 milliliters. But we need that to be liters, so we're going to convert to liters. And the milliliters cancel out. And the 10 to the minus 3s cancel out. So you can do it this second way. Some of you have gotten good at converting between milliliters and liters in your head, and that's also an acceptable way to do it. Instead of writing down 22.87, you write down 0.02287 liters, and that works as well. Or you can just do what I did in the first place. Any questions?
So you're saying liters canceled out in your first example? I thought milliliters we need to cancel out.
Well, but this liter and this liter canceled, but this one was left.
No, on,
Oh, and the first one?
yeah.
The
didn't
liters
cancel out,
didn't. The liters,
milliliters canceled out,
the
right?
milliliters canceled out, the
Okay,
liters
that's
didn't.
it.
It's just, it's kind of, yeah, I'm sorry, yeah. That's my goal, is to confuse you. Any questions?
Is the test still gonna be Tuesday when we come back? Thursday?
She's awesome. Tuesday she wants to do a review, and then Wednesday she'll be at Starbucks.